Welcome back. Let's tie all of the information together to see if we can use it to sketch the graph of a rational function that looks a bit more complicated. Now, of course, you can use your TI to check, but just in case, a lot of times you can't predict just by looking at your TI what horizontal asymptotes are or what slant asymptotes are. So we really want to analyze this analytically, which means let's do all the math and everything by hand. The other thing is sometimes you're not allowed to use a calculator, so you might as well learn some of the key points about this. So I'm going with a few steps and I'll kind of add in my own. The first thing they want us to look at is when you're dealing with your graph of the function or your equation given, let's see if we can find intercepts. So we'll go with that. Intercepts. Let's say x-intercepts first, maybe? That's a good idea. Okay, so if I'm looking to find the x-intercepts, I'm going to set the y value equal to 0, and that means it's f of x. Same thing. And if that is the case, what happens is we get, I'm going to probably have to use a little bit more of the screen, but I'll move over for you. That's going to leave us with 0 equals the entire rational function and we know from a little bit of algebra that if a rational function is equal to 0, it really means that the numerator is equal to 0. So that leaves us with x plus 2 squared times x minus 2. So if we have two factors that are equal to 0, we use the zero factor property. You can set each factor equal to 0, and we'll pay attention to the multiplicity in a second or so. But really, you're just looking at a double factor. So that's x plus 2 equals 0, or x minus 2 equals 0. So we end up getting two x-intercepts, x equals -2, or x equals +2. So right away, anytime I find information, I like to include that on my graph. And I do have a coordinate system below. I'm not too confident with where the axes are, so I'll draw them in a little darker. I suppose you can put them wherever you'd like. But for purposes of demonstration, we have our x-axis and our y-axis. And so right away I can plot where my intercepts are. X equals -2 and x equals +2. Now, the other thing you want to pay attention to is the multiplicity of each factor in the numerator. So again, if we look at the x plus 2, we got the x-intercept x equals -2 from this. And notice that the multiplicity is 2. So that's an even multiplicity. And with an even multiplicity, at x equals -2, you either have the case where you're tangent to the x-axis. So tangent means you're going to bounce off. You're either coming from the top and you're bouncing off. I'm just exaggerating at the moment. May not bounce off as that much. Or it could be that you're coming from the bottom and you're bouncing off somehow. Now, take a look at the x minus 2. We got a factor of x equals 2 from that. And you can't see the multiplicity, but it is implied that it's 1. And 1 is an odd number, so that means your function crosses through the x-axis. So it either comes from the top or it comes from the bottom. So I kind of have u's and x's going on to help me out. And we'll fill in the information as we go. The next thing I want to do, let's look at our y-intercept. And to find that, we're going to set our x value equal to 0. And if we do that, we're really calculating the function evaluated at 0. So if I'm looking at each of the factors, I include, I'll do this by hand, might as well. I have x plus 2 squared, that's 0 plus 2 squared, 0 minus 2, 2 times 0 minus 1, and 0 minus 3. So we clean this up just a little bit. I have 2 squared, which is 4, times negative 2. I have a 2. Negative 1 squared is a positive 1, and I have multiplied by negative 3. So feel free to reduce or simplify as you'd like, but I do have negative divided by negative, so I know I have a positive y-intercept, and then I can divide out the 2's. So I really have 4/3. So what's going on? 4/3, if you'd like to, you can end up changing that improper fraction to a mixed number, just so you can estimate where this is. 4/3 is approximately 1 1/3. So what happens? Let's plot that. Y-intercept, 1 1/3. We can estimate it's approximately over here somewhere. So at least we have those plotted. The other things we will do at this point is now address our asymptotes to help us out with the rest of the problem. So let's look at the vertical asymptotes and if we have any potential holes anywhere. So if you don't mind, I'll do some erasing at the moment. Leave myself a little more room. And I'm going to look at, I'm just going back to what's suggested. Let's go with vertical asymptotes and holes. And vertical asymptotes tend to come from the factors of the denominator and whatever makes the denominator 0. So what I'd like to do is kind of label. If I'm looking for my vertical asymptotes, I'll set all of the factors in the denominator equal to 0. And again, we'll pay attention to the multiplicity in a second. So I have 2. That's a more of the stretching factor. We'll deal with that in a second, or maybe a few minutes. But I do have x minus 1 equals 0, which gives me x equals 1 as one of the vertical asymptotes. I also have x minus 3 equals 0, which gives me x equals 3 as the other vertical asymptote. So this is kind of nice, so I can draw them right away. X equals 1. I'll indicate with a dashed vertical line. And I might label it as well, x equals 1. Also, what I'm looking for, x equals 3. That is located really close, actually, by. So x equals 3 is okay over here. We might have to expand our graph a little bit for that. So x equals 3. Now, what's going on is we'll pay attention to the multiplicity of the factor next to the denominator, or in the denominator. So x equals positive 1. Let's look at its corresponding factor. I'll erase that underlined by the 2 as well. Okay, so we have the corresponding factor, x minus 1. And we'll notice that the multiplicity is 2. And 2 is an even number. And again, I'll circle that. Now, whenever you have an even multiplicity, what's going to happen is your behavior around the asymptote as you're approaching from the left or as you're approaching from the right, the behavior should be the same. So they're either both going to, f of x will approach positive infinity in both cases, or f of x will approach negative infinity in both cases. So I'll say left, right, or left, right. So if you could kind of look at this, and you can kind of test this out if you're interested. Just the way your y-intercept, the location of your y-intercept, and the location of your x-intercepts, you'll kind of notice that as you're approaching from the left side, so maybe I'll even kind of help with this. As x approaches 1 from the left, you could kind of tell what's going to happen. Because you have a y-intercept, there's really, and you have an x-intercept here, you could kind of see that you might be doing something like so. So I'm suspecting that my graph is going to rise up to positive infinity. So I'm going to guess that f of x is going to approach positive infinity. And if you're interested in verifying this, and we would normally do this, you could pick an x value around x equals 1. So if you wanted to plug in, and I'll let you do this on your own time, if you want to test it out, I'll write it in black. You could test out x equals maybe positive 1/2. And then you can plug this into the function, and you can kind of see what type of y value do you get. Is it going to be a value of y above the x-axis, or a value of y below the x-axis? And just by behavior-wise, and you can kind of see where the y-intercept is, it will be a value above the x-axis. And you'll probably be relatively high, or high enough so that you can determine what's going on. So that's kind of something for you to verify on your own. Now, because we kind of determine what's happening from the left side, and we know that the multiplicity is even, we'll automatically come to the conclusion as x approaches 1 from the positive side, that's also going to tell us that f of x should approach the same positive infinity. And that'll kind of give you an indication. It helps you out kind of figure out what your x-intercept's doing. Got a little bit more there. Okay, I have an excited dog by me, but we're just doing some pre-calc. So let's go and understand that if the function has to approach positive infinity, most likely what's going to happen, we'll be crossing through. And if we're approaching positive infinity, I'm seeing something happening with my graph this way. So just with this information, you could kind of start completing what's supposed to happen based on your multiplicities of the x-intercepts around this area. Remember, one of the x-intercepts was at positive 1. See if I can highlight that in red. We already know that it was supposed to cross through, and based on the behavior of around your asymptotes, or the local behavior, you can probably continue the function where you're crossing through. So we can now erase the extra orange piece. The other part, again, when you're looking at x equals -2, let's see where that is. Right here. Okay. The behavior of our function around the asymptote kind of leads us to believe that we now aren't going to go below the x-axis. We're going to be tangent to it. So I'll erase that other piece. So I'm assuming that we're going to have something like this happening. I'm exaggerating. I know it's going to get really close to the x-axis, but we'll go from there. Now let's do the same thing around x equals 3. Again, the corresponding factor for x equals 3 is x minus 3. And you'll notice that its multiplicity, you don't see it, but it's implied to be 1. And that leaves us with an odd number. And so that tells us that the behavior is going to be different around that axis. So let's see what we can do there. I have, if I can look from there, it appears the way my function is approaching, and of course you can test this out for yourself. If you're going to approach x, as x is going to approach the, what is it, 3, from the negative side, that might be nicer. You can verify for yourself, what is f of x doing? Well, according to our behavior of our function, most likely f of x is going to approach negative infinity, basically because it has to cross to the axis and go down. If you're not sure what's happening there, what you can also do, just like I would do, is test a point right before the positive 3. So maybe test x equals 2.5 and then see what type of value you get. Do you get a positive value or a negative value? And it should be a negative value based on the behavior that you have to cross through the x-axis based on the multiplicity. But it'll also give you a verification of a nice point along the way. Now, if we know our multiplicity of that denominator factor is 1, that means our function is going to approach opposite infinities. So we automatically know as x approaches 3 from the positive side, that's going to tell us that our function must approach positive infinity. So something's happening up here. We don't quite have verification here, but I do have a feeling as far as rational functions are concerned, if you didn't find any other x-intercepts or asymptotes along the way, it means that your function is never going to cross below that x-intercept, or excuse the x-axis. So I'm assuming what's happening is we have something where little behavior that we're not going to cross over. So we'll verify this again. Maybe we have a horizontal asymptote coming our way. Let's see if that works. So let's go from here. Horizontal or slant asymptote. So let's do that. There's a couple ways to go. What I like to do is consider like an estimate of the function, kind of using, it's called like a dominant term analysis. So if you don't mind, I'll do some more erasing. A little bit, just want to clean it up so you guys can see the viewing window. Keep this in there. So what they always tell us to do, it's really nice to eventually when you get to calculus, you'll use this when you're calculating limits at infinity. We use dominant term analysis. And sometimes you'll hear me, if you take my calculus class, we call it the Bill Gates principle. And, you know, just stay tuned for why we call it that. It's kind of interesting. But what they like to do is just kind of consider f of x can be approximated by calculating the dominant factor in each of the factors. So in the long run, for really big values of x, this plus 2 and this minus 2 and this negative 1 and negative 3, that's not going to make any difference with the function as far as what's happening for very large values of x or very small values of x. So they like to talk about this as, let's just look at the factors with the values of x's and do some calculations there. So notice I kept the stretch factor, the 2 involved. That doesn't really affect anything according to what we're looking at. But what we do is we take the dominant terms and we just kind of do a little bit of mini math here. So f of x is approximately equal to x squared times x cubed. Let's see if I can write that in nicer. Over 2x cubed. And then you notice that if you reduce the x cubes out, you end up getting 1/2. So for very, very large values or very, very small values of x, your function is going to approach the constant 1/2. And if I could draw that in, the constant 1/2, that's actually your horizontal asymptote. And to kind of give you the reasoning why, if you like, you can go through. If you were to multiply the entire function out, I don't recommend that you do it. You can, it's not too big of a deal, but it's kind of a waste of time because you're focused on other things. You use this dominant term analysis. The leading terms are going to be found by just taking the leading part of each factor, the x part of each factor. And it actually ends up becoming that we focus on this part. Oh, I should probably not have an eraser. There we go. And remember, with the horizontal asymptote, you compare the degree of the numerator with the degree of the denominator. And we both notice that they have the same degree. So degree of numerator equals degree of denominator. And according to our calculations, if we have that case, then the horizontal asymptote is given as, and actually I already labeled it so I don't have to write this again, y equals leading coefficient of the numerator, so in our case it's a 1, over leading coefficient of the denominator. There's the 2. And so this kind of gives you two different ways that you can kind of consider the horizontal asymptote. And it really has to do with a little bit of dominant term analysis, or what we call the Bill Gates principle. So either way, you have your horizontal asymptote, y equals 1/2. So that would be kind of hard to determine what would be going on if you were just trying to straight graph this off of your TI. Now, this also helps me verify what's happening with my values onto the right of x equals 3. I know for sure it's never going to cross because I knew about the multiplicity on the right side. And I do know it crosses the horizontal asymptote. It has to, because if you have a y-intercept of 1 1/3, that's over here, and an x-intercept of -2, you do have to cross. So we can kind of verify that. We'll probably be getting really close to x equals 0, but not quite touching. And we know we're not touching it based on the multiplicity of the factor x equals -2. So I like to repeat myself a lot, but it's really helpful to understand. So you can kind of see that when I drew it, I wasn't quite sure. So if I can help myself, I know I'm probably getting closer and closer without touching the x-axis. So this should help us determine. I always double check if you are not sure about end or local behavior, do a lot of test points around your asymptotes. So like I said earlier, if you're not sure what's happening for very, very large values of x, the right-hand side of the graph, you may want to consider maybe testing. What happens when x equals 10? If x equals 10, most likely it's happening at x equals 1,000. And if it's happening at 1,000, it's probably happening at positive infinity. So that's what they talk about, the end behavior, or behavior in the long run. You can do this if you think you have the table in the graph, or you can actually manually compute it on your own. The other thing, again, if you're looking at end behavior, you can also test the same idea. What's happening at x equals -10? And if it's happening at x equals -10, it's probably happening at x equals -1,000. And by that argument, if it's happening at -1,000, it's probably happening at x equals -infinity. So I encourage you to try that and verify for yourself. But the information, just by knowing asymptotes, knowing the degree of the factor that's leading to the particular asymptote for the vertical asymptotes, and noting your degree of your factor for your x-intercepts, that gives you a lot of information of your graph already. So that's a really cool thing. I think we have a pretty accurate graph. Again, if you're not sure, like sometimes you may be interested in like, what's happening over here? Is that really a point? You may say, well, I don't know. Let's test it out. 1, 2, 3, 4, 5. What's happening at x equals 5? So you can say, well, at x equals 5, we can plug in f of 5. For wherever we see x. And you can do a mini computation. So 5 plus 2 is 7, so we have 7 squared. 5 minus 2 is 3. 5 minus 1 is 4 squared. 5 minus 3 is 2. Take a little time. We have 49 times 3. 2 times 16 times 2. We might not get something perfect, but you might want to consider what 49 times 3. Get out your calculator if you have to. We have 147. 2 times 16 times 2. I got on my calculator, 147 over 64. If you're not sure what that is, do an approximation with your calculator. And you end up getting something like 2.29 or 2.3 if you want to approximate. So you can kind of see like, oh, it's pretty close. 1, 2, 2.3. We can get a clear point on the graph. So, I don't know how necessary it is. It depends on if you're missing your TI, if you don't have it. But anytime you're not sure about a graph, picking a bunch of x values, plugging them into your y value will give you a lot of information about what's happening along the way. So just to verify, let's take this on our TI just so that you can see, are we pretty accurate? So let's pull up our smart view again, and we'll enter this in. Remember, if you're entering this in, it looks like the numerator has more than one factor. So we're going to have to, you'll probably have to squeeze this in, but play along with me. Open parenthesis, do another open parenthesis for the x plus 2 factor. We take this to the power of 2. We have x minus 2. And then we're going to close all of the numerator. Use division sign. Open the the denominator. And then we look at our stretch factor. That's a 2 in the denominator. And then we still have x minus 1. You might not be seeing everything, but it will go from there. X minus 1 square. Make sure you press that exponent key, otherwise it turns into a factor. And then we have x minus 3 factor. Make sure we open that parenthesis. You might not be able to see everything on the viewing screen, but I'll try to scroll over so you can. So I'm closing off the x minus 3 and closing off all of the factors in the denominator. So let's see if I can sort of move over. A little hard. Now, we press graph. And you notice we're pretty accurate. So let's copy that over and see what's happening with what we graphed. So I'll kind of paste it over here if I can. Although sometimes it ends up in a different place. So let's see. Let's try pasting it on the side. Sometimes that's something. Maybe not. Oh, we lost it. All right, so we're just going to have to use our imagination. Let me undo that for a second. Let me see if I can try one more time. I'm really interested in comparing them side by side, but maybe I'll just switch off so you all can see. Okay, so look at that. Oh, you can't see it anymore, huh? Let's go from there. Try one more time. I always like to really verify, am I doing this? See if I can paste it over here somewhere. Okay. This is just me talking to myself, but I would like to move things. Let's see if I can. Aha! We found it. So let's just take a look. I'll put it right nearby. And I'll grow it just a little bit for you. Now check it out. That is pretty darn accurate. And that's just all by knowing end behavior and multiplicities, intercepts, and vertical asymptotes. So I encourage you, practice these. It's really, really cool that just by looking at the equation of the function, you can get a really accurate graph if you know a little bit of information about all of these degrees, multiplicities, and end behavior. I hope this helps. I'll see you in the next example.